Okay, so we've been talking about things that oscillate or go back and forth, right? And one of the tasks that I asked you to do was we did a lab, and in the lab there was a pendulum. And the pendulum swung back and forth and back and forth. And we took a video recording of this. This was like the week before we left for our Easter break. And what I had asked you to do in the computer lab downstairs was record the pendulum going back and forth. And you hopefully had a large table of values which had, I think, X in one column and T in another column. And when you eventually plotted that data in your graphing calculator, it hopefully went like this, up and down and up and down. And I'm in the process of marking that lab right now, but from what I can see, it looks like most of you are able to plot that data going up and down. And we used something called a sine regression. So hopefully that's not absolutely brand new to you. What I want to do today is elaborate on that, because anything that fits the sine regression pattern that goes up and down, that oscillates back and forth, we call it a wave. And there's a huge math overlap. For any of you who are currently taking Math 30, if any of you are in a Math 30 class right now, or for any of you who are planning on taking a Math 30 class, there's a whole unit devoted to talking about the graphs of things that go up and down. This is known as a sine wave. And that's my goal of today's lesson, is to talk about the theory behind that. So to begin, I've just got a picture of a surfer here. And often when we think of the word wave, I think in a non-physics context, we think of a wave, we think of water going up and down, right? There's supposed to be a new swimming pool over here at the YMCA. I don't know when it opens, but soon, I think, right? And I believe it's supposed to have anybody know when it opens, by the way? Saturday, sweet. My girls want to go on the water slide so badly, so. But I think there's supposed to be a wave pool in that new swimming center, right? And so when I think of waves, I think of waves that go up and down, up and down. Yes. Now, that is one type of wave. Like, that's not wrong. I mean, a wave of water that goes up and down, that is definitely a wave. But what I want to introduce you guys to today is the fact that there are many different types of waves. There are waves that come in the form of radio waves, microwaves, X-rays are a type of waves. This big spring that I have across the classroom, it can also produce a wave. Water can produce waves. I am currently speaking to you. You are hearing sound waves. So the main goal of today's lesson is to discuss all the different types of waves that we have discovered, I guess, for lack of a better word, and some of the theory behind it. So the first definition I have is the one down here at the bottom. A mechanical wave is any sort of wave that travels through a medium. Okay. And that's probably where we need to pause for a second and discuss what the heck a medium is. Okay. A medium would basically be like the stuff in which something might travel through. If I take this spring right here, and I basically have it start vibrating back and forth, I've now made a wave out of it, but that wave is literally traveling through the metal in this spring right here. And so that's known as a mechanical wave because something is physically moving up and down. However, we have something called, why don't we go with radio waves? Your cell phone is probably picking up something in the radio waves or microwaves spectrum of electromagnetic radiation, and it doesn't need to travel through a medium. Neither does light, for example. Light does not require traveling through a medium. There are waves of light being given off by these light bulbs, and yes, although they are traveling through air, they don't actually need to. We know this because light travels to us from the sun through outer space, and there literally is nothing in space. There is no atmosphere there. There is a vacuum in outer space. And yet, light waves manage to travel through it. So there are some waves that need an actual physical object to vibrate up and down or back and forth. And then there are other waves that apparently don't even require a medium through which to travel. So I'm going to start by talking about the mechanical waves. Any sort of wave, though, whether it's mechanical, whether it's a wave that doesn't require a medium, it always has that up and down pattern. And by the way, is anybody currently in a Math 30 class right now? Okay. You will be at some point. This is a slide that I pulled out of my notes back when I used to teach Math 30 back at Walsh. This is basically the pattern. It goes up and down and up and down. And if you were ever to take your graphing calculator and type in y equals sine x, as long as you set the settings right, it'll have that wave function to it. So my next few slides are going to talk about some of the properties of these graphs, these ideas of waves going up and down. The first thing I need you to be aware of is that in math, we often work with degrees, but your calculator will likely need to be set into radians in order for it to work properly. I'm not going to give you like a full lesson on what the heck radians are, but I just need you to be aware that if you ever do a regression in your graphing calculator and you plotted data, did anybody come across this where you plotted all these data points and then you were trying to put the sine regression through it and it put a line that kind of went like that and it didn't actually work properly? And then maybe I would have told you, hey, quick, change your calculator to radians. All of a sudden, then the line that went through all your data points actually went up and down. That's what I just wanted to notice here, is that we can measure things in degrees, but chances are radians is what we're going to measure along the x-axis. And so that's what this graph will look like here. We often do that in math. Math we often measure based on degrees or radians. However, in physics, we're often along the x-axis going to measure something either known as the period, which we've discussed already, or today I'm going to introduce a new concept called a wavelength. And I think the best way of describing that is just going to my next slide here. Okay. So here's that same kind of picture. It's a wave going up and down, up and down, up and down. Well, when we want to measure how far it is from here to here, like let's say we go from the top of the wave to the top of the wave, one of the ways that we can quantify that amount is by a distance. We can say, how far is it from here to here? And from here to here, that distance, which we would measure in meters, chances are, we can measure it in centimeters, we can measure it in micrometers, but chances are that distance is in meters. We call that a wavelength. And the symbol for that is this funny looking Greek symbol called lambda. Lambda. And if I could now use the wave that's right here, imagine that I were then to like make this wave go up and down. I should stand on one of the edges though, so it looks better. So imagine I were to make a mechanical wave by vibrating this up and down. So I've got it kind of vibrating up and down. Now, you're gonna have to kind of envision where the tops and the bottoms happen to be. But can you kind of see how right about here is where the top of the one wave is? And then the wave hits the top again somewhere over there by John. You guys agree with that? Like over here by Riley, this wave as it goes up and down, the very, very top of the wave, it hits the peak right about here, right in front of Riley. And then it hits another peak somewhere over there just next to John. If I were to then, stop this thing from vibrating, it was at its peak right about here. It went all the way down, and then it hit its peak again over here. If I were to literally measure from here to there how far that is in a wave, we call it a wavelength. Okay. Now there are some waves that are very long. The wave that I just made go up and down was a very long wave. But radio waves and microwaves and X-rays, they have shorter wavelengths. Often they're much shorter. So short sometimes that they can penetrate the human body. X-rays have a wavelength that is so small that X-rays can actually go through like flesh. They don't go through bone though, which is one of the reasons why when you get an X-ray, you get like the white for when like an X-ray runs into bone. But otherwise you can actually have X-rays pass through things because they have such a small wavelength. This wavelength of the big spring going up and down though was quite large. Now that is one of the ways that you can measure a wave. You can literally measure a distance from the top to the top and then tell me how far that happens to be. Another possibility though is you can measure how long it takes for this point right here to turn into this point right here. So rather than measure the distance that it is from this point to this point, you could measure how long it takes to get there. Let me try the exact same thing again. I'm going to make the spring go up and down. Again, focus on the heights. So at this point right here, where it's very high by Riley, and then over there, when it gets high again to John, we could measure how long it takes for that to change. Watch, I'm just going to actually ripple this up once. I'm going to go there. Ooh, maybe I actually have to make it go up and down like this. Hang on, let's do this. There we go. Okay. Can you guys see how the two peaks there, it's going to take a while for this peak to turn into that peak? If I were to do like a slow motion capture, it's like right now it's at the top, and right now it's going to be at the top again. We could actually measure the amount of time that it took for the spring to go all the way up here, all the way down here, and all the way back up here again. Can I show you that again? We could measure not only the distance, but the time it took for this to go up, then for it to vibrate back down right about here, and then for it to come back up again. We can measure the time it takes to do that. And so, I mean, since it's going to oscillate continuously, we call that time the period. So there are two different ways then that we can measure a wave that's going up and down, either based on the distance between things or the time between things. Does that make sense? Now, let me give you some more definitions of waves. You'll learn about this in a math class at some point, but I may as well show you now. We have better terminology than what I just said for like the top of the wave and the bottom of the wave. If you ever have a high point on a wave, we call it a crest. And if you ever have a low point on a wave, we call it a trough. So there you go, right? As the wave was going up and down, if you can kind of recall the wave, over here by Riley, we were getting crests. And then over there by Ethan, we were getting troughs. And then over by John, we were getting crests again. Can I show that one more time and then just make sure we're clear on the terminology? So I'll make this thing go up and down again here. All right. The highest point of the wave, we have two of them. I think I have a high point up here. Well, actually, I should take that back. We actually have a high point that turns into a low point. Over by John, we have a high point and a low point as well. Another term I need you to know, though, is the word node and antinode. A node is when the wave is like right in the middle at the equilibrium position. I need to make this thing not vibrate so violently. Here's some more terms we can use. If the top right here is a crest and the bottom right here is a trough, a node would be when the thing is right here, right in the very, very middle. I think I was describing that poorly. This wave was going up and down right here, and then the wave was also going up and down right here. But right in the middle, right about here, if I move this thing again, you might notice that this point right here almost doesn't move at all. Does that make sense? Like this was going up and down here. Over here, this was going up and down right here, but right here by Ethan in the middle, the wave was actually like, there was almost like a stationary point. We call that a node. Let me try to make this wave one more time here. Can you guys see how right in the middle of the wave, there's probably a section, if I could stand up and make this, here, see that I can. One of you guys want to kind of just do this for me so I can go move by the wave? Can you just like vibrate this up and down? Just a little bit. Yeah, just keep doing that. Okay, now I can go over here. Can you guys see how there's a point? Oh, you just got to get it right back again. Yeah, there's a point right about here where, can you see how this point right here is hardly moving at all? Right, it's moving a little bit, but it's not really moving much at all. This point right here is clearly going up, down, up, down, up, down, right? This point way over here, clearly going up, down, up, down, up, down. But right about here, somewhere in the middle, there's a spot where minus a little bit of wiggling, is this moving all that much? No. You can stop now. Thank you. That was perfect. So in terms of terminology, let's go back to our terms. Crests are when something's at the highest point it can be at. Troughs are when something's at the lowest point it can be at. Nodes then are right in the middle here. These four dots right here are called nodes, and they're always halfway in between. There's always a halfway point between the highest of highs and the lowest of lows that we call a node, and we call that the wave at the equilibrium position. See how the slinky right now, the big spring, is no longer being moved, right? Well, that's where this point right here was more or less just stationary. This is the equilibrium position when it's not moving at all. Antinodes then, so let me just label these. These guys right here would all be your nodes. Antinodes are just a fancy word for your crests and troughs. Oops, what did I do? So this would be an antinode. 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 All of these tops and bottoms right here, these guys right here would all be known as your antinodes. So now we can use the same vocabulary. As a wave goes up and down and up and down, highest of highs, crests, lowest of lows, troughs. Nodes are the points where nothing moves, and we can then measure this wave in a few different ways. We can measure how long it takes for the high right here to become a high right over there, or we can measure how far it is from the high of highs to the high of highs. But let's not call it that. Let's call it crest to crest. Does that make sense? Another term I need you to know is amplitude. And amplitude is how big the wave is. So when I'm shaking the spring up and down, if the spring just goes up and down just a little bit, it has a little bit of amplitude. But if the wave goes higher and higher, it has more amplitude. I could make this exact same wave like this. See, I could make a wave that looks like that, but this wouldn't be as powerful of a wave. If we're talking about sound waves, Amplitude is how loud they are. Does that make sense? If we're talking about light rays, it would be how bright they are. And so in general, amplitude of a wave is related to how much energy it has. I'll just put a little note here. Sound waves would be louder. Light waves would be brighter. So if we can make these waves oscillate higher and higher, then that's how much energy they have. We've actually talked about this concept before. How do you make a wave get bigger and bigger and bigger and add more amplitude? What's the word we gave to that back in like topic 3? Anyone remember? I didn't hear it yet. What did you say? Resonance. Good job. Yeah. When you have a natural frequency matched by a resonant frequency, you can make the waves get bigger and bigger and bigger, right? As I was basically making the wave go up and down, as long as you manage to get it in the same pattern, up and down, same pattern up and down, if you match that resonant frequency perfectly, you can make the wave bigger and bigger and bigger. So the word we use for that is amplitude. Basically, that's how tall it is. So. Okay, and then here's a slide that again discusses how we measure things not in the up-down direction, but in the side-to-side x direction. You can either base it on how far it is, known as a wavelength, represented by this symbol right here, known as lambda, which is called a wavelength. Or you can measure by how long it takes time-wise, which we measured in period. However, anything that has a period can always be turned into a frequency. Remember how period and frequency have that relationship? So I could actually tell you how frequently these waves are going up and down. We've actually talked about this already. Here's a couple of different waves. Which wave has a higher frequency? The top one or the red one down here? Which one has a higher frequency? The top one, because the top one went up and down 1, 2, 3 times. This one had a frequency of 3 times, basically, right? This bottom run right here went up and down once and maybe half of it. This one had a frequency of like 1.5, right? Frequency is how often something occurs. So if you take a look at a wave, if you have a wave that like is really long and stretched out, it's not a very frequent wave. If you have a wave that's going up and down, up and down, up and down, and just humming along, like let me just do one more as an example. Let's say that I had a wave that went up, down, up, down, up, down like this. This right here would have a very high frequency. And the reason why it has a high frequency is that it has a very low period. The distance between these points right here is very low. If you have a low period, you're then going to have a high frequency, which is why this thing's humming up and down so much. So hopefully you're starting to understand a few of these like terminology words we give to waves. Now, when we have waves that are going back and forth, sometimes a wave is like what I've been doing with this big slinky across the room. It just goes up and down, and it goes in one direction. But sound, as an example, sound doesn't just go just in one direction. Sound goes in all directions. It emanates out in 360 degrees. And so sometimes what we rather do is draw what's known as a wave front. And this is a picture of a diagram where imagine that right in the middle here is something giving off waves. I don't know what kind of wave it's giving off. It could be water waves, it could be light waves, it could be sound waves, but it's emanating off in all 360 degrees. What's happening in this example here is that all of these concentric circles all represent the crest of the wave. And so if you can kind of imagine this, this right here would be a wave being given off, and here it is at its highest. And then it's going to be at its lowest. And then at its highest, at its lowest, at its highest, at its lowest, at its highest. And this is a wave that was taking off basically in that direction. But waves don't just have to go in one direction. Sometimes they do, but sometimes waves go in all directions. So here could be that same wave going up and down and up and down and up and down and up and down. And you'll notice that every time I hit the top of a wave, a crest of a wave, I always put that on the line. Okay. And so this is kind of a picture as though it's like a top-down view of a wave. If you can imagine that, like I was making this wave go up and down like this, but it wasn't just going just in one straight line. It was also going that way and that way and that way. So imagine that somehow I had like a whole bunch of slinkies around the room, tied up here and there and there and there and there, and I made all of them go up and down simultaneously. That's what this picture would be as though you looked at it from the top down. And I think these pictures right here on the next slide give maybe a better view of it. Imagine that you just took just like a ball of something like that and just dropped it in the water. Can you imagine how there would be ripples in the water afterwards? And you can kind of see here how the ripple, this is going down and then back up, and then back down and back up, and then back down and back up. Can you see how there's kind of like these waves right here? As it emanated out in 360 degrees, the wave front, we just draw the highest points. And so every circle that we draw kind of refers to the high point on the wave everywhere. And in the middle between the circles, right about here, this would be where the lowest point, the trough of the wave is. So if I can try to draw this one more time. As this thing comes out, this would be the low, then you'd have the high, then you'd have the low and the high, the low and the high, and that's basically what these circles emanating out refer to. Here's an example of like a radio tower sending out signals, right? Does a radio tower send a signal just in one direction? Well, no. You can hear a radio signal like anywhere in the nearby vicinity. So if I were to try to draw this again, this would be the highest point on the wave. Here would be the low. Here would be the highest again. Here would be the low. Here's the highest. Here would be the lowest. Here would be the highest. And it would do this in all directions. So we call that a wave front. And that's essentially what this picture right here is used to illustrate. Like I said, most of our lesson today, even the rest of our unit, there's not a lot of math to it. It's more or less theory and understanding about how waves work, this up-down oscillating motion. So, anyone have any questions so far? Okay. Now there's actually two different types of waves. So far, I've just been showing you with the spring here what's known as a transverse wave. This wave that I'm basically making go up and down, this is known as a transverse wave. Let's see if I can get the timing right here. Well, actually, even if I do this, that's not bad. Say I just did a wave like this. Can anyone tell me where the antinode is in this wave right here? Whereabouts is the antinode? Yeah, John's right. It's right in the middle. Where are the nodes? On the two ends, yeah, right? These two ends are kind of the nodes, right? Now, is this wave right here, does this wave have a long wavelength or a short wavelength? I'd say very long. Okay. Now watch this though. What if I could kind of speed things up and get it going back to where I had it before? If I can get the timing back again, do you see how now the wavelength is now half as big? Because now the wave has a node here, it has a node in the middle, it also has a node at the end there, and now the wavelength has been cut in half. The reason why it's been cut in half is that I'm increasing my frequency. There's now two waves here. There's a wave here on the left-hand side of the room and on the right-hand side of the room. But if I go slower and do a slow wave, so let's try this again, just one slow wave, right? This is not as frequent of a wave. Okay. Now, if I was really good at this, maybe I can actually get like 4 waves inside of here. I'll see whether I can even do that. I gotta get the timing right. You can see that I'm not timing it right. But if possible, maybe I could get 2 or 3 waves inside there. Oh, I almost had it there. There we go. Can you see that there? It might. John, can you make sure that that one over there doesn't fall over? Can you just be my guide there? Here, let me try this one more time because this is kind of cool. You need to see this. I'm going to try to have a wavelength be the whole classroom. Here's a wavelength that's the whole class, right? It's all the way from me to John on the far side of the room. Okay. That is a very, very low frequency, but a very high wavelength. And then if I try to increase it, maybe I can make a wave that looks like this, where now there's a node in the middle, basically where Ethan's sitting. Right? Now if I try to go even faster, I just got to get the timing right. Nope, still don't have it. That's not bad. Can you guys see how now there's actually 2 nodes in the middle of this here? So long as I don't whip somebody in the head there. There was a node basically right about here, and then there was a second one right here because now the frequency was 3. Okay. Thank you, that's all I needed just to make sure it doesn't break. That was known as a transverse wave. Transverse waves are waves that go up and down. Most people are able to visualize transverse waves because I literally just made one right here at the big spring. But there's actually a second type of wave. It's known as a longitudinal wave, and it's actually what happens when I talk. Sound is an example of a longitudinal wave. There is no air molecules vibrating up and down as I talk. It's doing this. It's more of a pulse. Watch this here. I'm not going to make this go up and down. I'm just going to give it a bit of a pulse. Did you see how it's pulsing back and forth across here? Let me try this again. I'm just going to make it go like this. And what's happening is there's a series of compressions and expansions. As soon as I push the spring in like this, there's always going to be a section in the spring where it's kind of pulled together like this, and it's basically going back and forth like this. That's known as a longitudinal wave, and the best way of me showing you one of these is I have an animation on the next slide. So maybe I should just go to that next slide now and show you the difference between transverse and longitudinal. Okay. Here's a type of wave that's basically going up and down, up and down. You can actually see that right here it's at its highest, and it'll again be at its highest maybe right about here, and right about here. You see how they all kind of match up in that same peak right there? So there's a crest here when there's one there, when there's one there. That's known as a longitudinal. This is a transverse wave up and down. This one right here is more like what sound is having happen, where there's a pulse and a pulse and a pulse. And you can actually see all of these molecules right here. It seems like they're moving, but that's not really what's happening. Look really closely at all these little dots right here. Just check those dots out right where I'm pointing. I'm going to shut up for a second. You just watch those dots. Are any of those dots actually themselves moving long distances? Like, look at this one right here. This one right here is going back, and it's hitting that one, which hits this one, which hits this one, which hits this one, which bumps some more on, right? But look at any one individual dot. Any one individual dot is actually just going back and forth just a little ways. But what's happening is as they kind of clump together in groups, they're hitting a whole wave front. And this right here, and this right here, and this right here, and this right here, those are all examples of wave fronts of pulses being sent out. It works a little differently than the up and down wave, but basically the logic is the same. The distance from here to here would be your wavelength, or the amount of time it takes would be your period. So I could say that it took 1 Mississippi, 2 Mississippi, 3 Mississippis. I could say the period was 3 seconds. Or I could actually go out and get a meter stick and say that from here to here is like 30 centimeters. Both of those are ways you can measure things. I can do the exact same thing up here. I could say it takes, how long does it take for this wave to go all the way up and all the way down? So 1 Mississippi, 2. Okay, so it took about like 1 second for this thing to go all the way up, all the way down, all the way back up again. Or I could measure how far it is from here to here. So, okay, hopefully I described that well enough. Sound waves then on my next slide are a great example of that longitudinal wave. What really happens when we speak is that the air molecules that you expel as you talk, they bump into other air molecules, and they bump into other air molecules, and they cause little reverberations throughout the atmosphere. If you were to try to talk, though, in a vacuum, okay, first of all, you wouldn't exist in a vacuum because your body wouldn't survive. But in theory, let's say that you could survive an environment where there's no oxygen, there's no nitrogen. You wouldn't be able to speak because there'd be no medium through which air particles could vibrate off each other, sending waves out. Right? If I were to knock on this table right here, one of the reasons why you're hearing that is that I just caused the molecules in the table to vibrate. And as those molecules in the table vibrated, they caused air molecules to start vibrating. And those air molecules started vibrating until you finally heard it. Right? That's what your eardrum basically picks up on. So we can actually tell how fast these waves travel in different mediums based on what they are. In air, sound waves travel about 330 meters per second. It depends on where you are. There's a lot of factors. Temperature, altitude, what it is makes a difference. But like sound waves do travel through water. But have you guys ever tried to like hear somebody like make some sounds underwater? Not that you can really fully talk underwater, but it sounds really garbled. One of the reasons why is that the speed of sound in water is very different than the speed of sound in air. Even iron, you can actually send a wave of sound through anything, right? This plastic, this metal right here, you can just put your ear right up next to it. You could hear tapping on it. What you're hearing is the vibrations inside the object, and they all travel different speeds. Okay? All you guys need to basically know then is when the amplitude gets larger, it's a louder sound. So if you have a wave that's going up and down like this versus a wave that's going up and down like this, the top one is going to be a louder sound because the vibrations are happening more violently. You can hear them better. So So here's another picture, again, just kind of reiterating what I've been saying here. What do you hear when you hear sound? You're just hearing particles compressing and expanding. You're hearing a whole bunch of them bumping into each other right here as this particle basically vibrates back and forth. As it's vibrating back and forth and vibrating back and forth, eventually there will be a compression of sounds. And eventually that's what you hear. Why don't I go back to this slide right here? I just want you to kind of watch the pictures a little bit, because this is kind of cool. I like this animation here. I think it's quite useful. Just watch individual particles. Make note of the fact that they're not actually moving that far. There is not a particle right here that is continuing to move the whole time. Right? What's really happening is this particle right here is bouncing from here to there, and from here to there. It's hardly even moving more than like a few centimeters on my screen, but it's making a wave front go outward so you can hear. Okay, let's move on, because I'm kind of saying the same thing over and over again now. There are other waves that don't require a medium to travel through. Now, we're going to spend an entire unit on this in Physics 30, but anything that's part of the electromagnetic spectrum is a wave that does not require an actual medium to travel through, because it's not like there's particles bumping into each other. Waves can actually travel through literally nothing. And so anything that's in this spectrum, and if you guys remember the electromagnetic spectrum from like grade 7 or 8 science, we're talking everything from radio waves and microwaves, visible light, all the way down to X-rays and gamma rays. These are things that do not actually require things to bump into each other, which makes sense because we get ultraviolet radiation from the sun, and it needs to travel from the sun to the Earth, and there is literally nothing for it to travel through. Right? There is nothing in outer space that it can actually cause particles to vibrate up and down or side to side on. And so therefore there's some things that don't require a medium. These ones by the here are considered transverse waves, but it's kind of confusing because there's not actually something going up and down. We believe there's actually electric and magnetic fields going up and down. And that's a conversation for Physics 30, I guess. So, in a similar sort of way then, we can actually quantify the electromagnetic spectrum based on frequency and wavelength. The wavelengths that are the longest are going to be your radio waves and your microwaves. Those are actually your longest wavelengths. Your shortest wavelengths are gamma rays and X-rays, these ones over here on this side of the spectrum. But the opposite happens for frequency. These are actually very high frequent waves, and these ones over here are very long frequent waves. In general, the longer the wave, the less dangerous it is. So these waves over here don't really cause a lot of human health effects. Like microwaves and radio waves, there are probably many microwaves and radio waves bouncing around this classroom. There's like probably at least 8 different radio stations in town that are giving off radio signals. Your cell phone is going to be picking up signals in both Bluetooth spectrum, in the Wi-Fi spectrum. If you have 3G data, there's at least 3 different signals coming to your cell phone probably in the microwave spectrum. Those are relatively harmless over here. But gamma rays, X-rays, and ultraviolet radiation, these ones that have high frequency, those are all quite dangerous to health effects. Ultraviolet radiation often causes skin cancer. If you guys have ever been to the dentist before and you have to get dental X-rays, what do they make you put on before they take X-rays? Yeah, the lead vests, because X-rays can cause cancer otherwise. Gamma rays are in the same thing there. So these ones over here, the word we've got here is it's called ionizing radiation. These are these are radiation waves that are quite dangerous, but these ones over here are not dangerous at all. Like light itself is not a problem. Ultraviolet radiation though is. Okay, let's move on to the last part of our lesson, and I should be able to wrap things up. There are a couple of formulas that we can use when it comes to waves. They are very simple. I'm going to show you one of them today. First thing I need you to know, though, is that when light is traveling, it travels the speed of light. Maybe you've heard that phrase before, traveling light speed. Scientists have been able to calculate how fast we believe light travels, and here's the number. It's 299,792,458. That's how fast we believe light travels. And Einstein had some pretty cool theories in the early 20th century based on what would happen if you traveled the speed of light. They involve things like time slowing down or speeding up, masses getting larger or smaller if you could travel the speed of light. But this is how fast basically we believe that light does travel. And it's denoted by the letter c in your data booklet. C is the letter we give for the speed of light, and you might recognize that because it's actually part of Einstein's famous formula E equals mc squared. All I need you to know then is whenever we need to work with the speed of a radio wave or a light wave or any sort of wave that's in the electromagnetic spectrum, it's traveling the speed here, 3 times 10 to the 8. And this is actually on your data sheet. If you check the constants side of the sheet, it's actually listed on there. The reason why we need that is that there is one formula that we can use. It's called the universal wave equation. And I've got basically some explanation in the first little bit here as to where it came from. But what we really need to be able to do is just know how to use this bottom equation. Here's the equation. The velocity of any wave is based on two things. It's based on the wavelength, which is how far apart those crests and troughs were. And it's also based on the frequency of the wave, which is basically how often the wave is occurring. If you basically take a wavelength distance and a frequency and times them together, we've discovered that is how fast the wave is traveling. And so we can do some basic equations. Now, before I go to that, I'm going to make the spring go up one more time here. If I were to be asked, how fast is this spring traveling right now? It's kind of hard to figure out how fast it's traveling because it's not like it's traveling in one direction. It's traveling up and down, but like even this point right here, this point really isn't traveling all that much. So if you want to find the speed of this wave, you need to know two things. One, you'd have to know the frequency with which I'm oscillating this. I think my frequency is about 1 hertz right now. It's going up and down about 1 time per second. Does that make sense? If I were to speed it up and try to do this, so I can get it there, I think my frequency is now about 2 hertz because I'm going about twice per second. Right? So that would be my frequency. The wavelength then would be basically how far it is from here to here, the middle. That would be how far the wavelength is. So if we have those numbers, we can solve some math equations. So let's try this and then we'll wrap things up. Practice question 1. Let's say that you have red light. And red light has a measured wavelength of 700 nm. N stands for nanometers. Okay. If you look on your data sheet, if you're not familiar with this, an N, which stands for nanometers, is anything that's times 10 to the minus 9. So red light has been discovered to have a wavelength of 700 times 10 to the minus 9 meters. I would say the wavelength of this wave right here that we just made must be like 8 meters, because it's probably at least 8 to 10 meters from one side of the classroom to the other. Probably more than that, probably shorting that a little bit. But red light, the wavelength of red light is tiny. It basically hops up and down within like, you can't even put your fingers close enough together to see it. So we actually know a wavelength. Well, I also know one more value here. I know that if it's ever in the electromagnetic spectrum, the velocity is also the speed of light, which is 3.00 times 10 to the 8. And so if I want to figure out the frequency with which red light oscillates up and down in its wave pattern, I just use the universal wave equation. Velocity equals frequency times wavelength. I'm then going to solve for the frequency by dividing both sides by the wavelength amount, and I'm going to make myself a new formula. My frequency will be equal to velocity divided by wavelength. The speed of any electromagnetic wave is always the speed of light, 3 times 10 to the 8 meters per second. And if I tell you that the wavelength of red light was 700 nanometers to the minus 9, all I've got to do is just divide these two numbers, and I should be able to tell you how frequently red light is basically going up and down. How often it does that in a second. I just need my calculator here. 3 times 10 to the 8 divided by 700 times 10 to the minus 9 gives me an answer with 3 sigdigs of 4.29 times 10 to the 15, and that would be in hertz. Okay, let's talk about what we just did. Like, what does that even mean? If you could imagine light being a wave that's going up and down, if light is a wave that's going up and down, what we've discovered is that the wavelength, the distance from one spot to the next here, is 700 times 10 to the minus 9 meters. So that means the distance from here to here is tiny. Well, the 4.29 times 10 to the 15 hertz means that every second, red light goes up and down, up and up, down, up and down a lot of times. Like, that's not even a million or a billion or a trillion. Like, that's even past that. It's to the 15. Basically, it's going up and down a huge amount of times in 1 second. Okay. Whereas the long wave that I made right here, it went up like once per second, maybe twice per second. So, that makes sense so far? It's a pretty easy equation. You just literally just type numbers in. This one's not usually one of the more challenging ones. Let's try another example. Let's try to find the wavelength for a cordless phone operating at 900 megahertz. So for any of you who have like wireless devices, they operate on certain frequencies. Cordless phones often operate on the 900 megahertz wavelength. So the M, if you're not familiar with capital M stands for mega. And if you check on your data sheet, it refers to anything that's going to the power of 6. So what I've now told you is that your frequency is 900 times 10 to the 6 hertz. But what's the velocity of this going to be? Well, the speed of light. So that'll be 3.00 times 10 to the 8 meters per second. Using my formula, which is velocity is equal to frequency times wavelength, if I want to solve for the wavelength, I'll have to divide both sides by frequency and get V over F. The speed is the speed of light. And my frequency was 900 to the 6. So I got a wavelength of 0.333 repeating. With SIGDIGs, I guess that's where it would end, 0.333 meters. So that means that if you have a cordless phone in your house, it means that the wavelength, if that's about a meter, you can't see it. But there's a wavelength that's oscillating up and down basically every this far apart, basically every 30 centimeters. There's a wave going up and down, which is actually a fairly long wavelength. Radio waves and microwaves are the longer of our waves, and then the really, really short, tiny ones are gamma and X-ray and ultraviolet. None of these we can see, by the way. The only electromagnetic waves that we have the ability to see are light waves. And that's because our eyes have rods and cones in them that allow us to actually see certain colors of light. We don't actually have the ability to see radio waves or to see microwaves. We can detect them, but we need other apparatus for that. So, I think that's my last slide. I'm just going to double check here. So let me do a quick recap here, and then I'll ask if there's any questions. What I need you guys to know today is basically two main things. No, let's say three main things. First, I need you to know all of the definitions we give to a wave. If I talk about a crest or a trough, if I talk about antinodes or the nodes that are in the middle, can you label those in a wave going up and down? Do you get that concept? You need to understand that vocabulary. You need to know what a wave front is. Okay. The second thing I need you to know is the difference between a transverse wave that goes up and down or a longitudinal wave, which is like a pulse that emanates outwards. They both kind of work in a similar way. One is up and down, one is a pulse, but you should know the difference. And you should also be aware of the fact that some waves actually require a medium to travel through, others don't. Right? But like if you were in outer space and you tried to talk, no one would be able to hear you because talking requires compression and expansion of air molecules. And if there's no air, then you can't hear anything. This wave that we made with the big slinky here is also a mechanical wave. Non-mechanical waves would be things like light, X-rays, gamma rays, anything in the electromagnetic spectrum. The final thing you need to be able to do then is use the universal wave equation. It's fairly straightforward. It's only got three parts to it. It's got a velocity, a frequency, and a wavelength. And the velocity is often the speed of light because any EMR wave, electromagnetic radiation wave, they all travel the speed of light. So if you're given a frequency, you should be able to find a wavelength, basically. And as long as you understand what a frequency is how often it's oscillating up and down, and a wavelength is how far apart those parts are, then you can do some math and solve for how fast it's traveling. Okay. Does anyone have any questions they can think of right now? That made somewhat sense? It's a very theoretical section. It's very visual. it's good that we can actually see an example of mechanical waves because you can't see sound waves. You can't see light rays, right? I mean, you can see light, but you're not really seeing them go up and down. Question? I can explain that. That's a great one. Okay, so you know how we've learned about the natural frequency of things, how everything has its own natural frequency that's vibrating? Microwaves are actually in the spectrum of the natural frequency of water. And so whenever you have food in the microwave, often there's an amount of water that's inside of your food, right? I mean, maybe it's not entirely water, but there's definitely a water content inside of most food. What ends up happening is when microwaves get bombarded through your microwave, it causes them to start vibrating more and more. And through the concept of resonance, it vibrates at the natural frequency of water. And so the water molecules start to vibrate a little bit more, and a little bit more, and a little bit more. And when things are vibrating up and down, that's also, I mean, it's loudness when it's sound, but when it's just particles vibrating up and down, it's heat. And so that's why microwaves heat up your food, is because they're set at the resonant frequency of water. Makes sense? Cool. Great question. If I can add another little anecdote here about microwaves. It's actually kind of silly that we use the word microwaves for them. Micro refers to things that are very small, right? Micro refers to things that are very small. And when you look at where microwaves are in this spectrum right here, I would not say that those are the smallest waves we have. Because wouldn't you say that gamma rays and X-rays, aren't those the smaller waves we have? And one of the reasons why is that when the term microwave was coined, those were the smallest waves discovered at the time. Because at the time we knew about mechanical waves, like this big spring going up and down. We maybe even knew about radio waves. Well, once radio waves were discovered, microwaves were smaller than radio waves. Right? And so that's why the word microwaves was given here. Eventually, physicists realized that light was actually a form of a wave as well, and so were X-rays and so were gamma rays. But since the word micro had already been given to whatever was smaller than radio waves, it kind of stuck. But it makes no sense that micro would actually be right here. I would think that you should put micro over here, because micro refers to small. But it's just based on when they were discovered. They are micro compared to radio. So. What was that? Exactly, right? I mean, well, we really should call our microwaves like food rays. Well, in terms, you know all the prefixes like micro and mega and kilo and deci? We should probably call them kilo waves, because many of the microwaves and radio waves fall in the kilo spectrum, in the, what else is above? You know how there's like milli and centi and hecta and deca? They kind of fall in that sort of range there. So micro would actually not be an appropriate word to use. But, okay. Anyone else have questions that they can think of on the topic while we're asking? Okay. I'll leave that there for now. Let me stop the recording here and then we'll chat for a bit here.